Now let's look at the sampling distribution of the mean. So again, this is the winter results. I can see the distribution is left skewed. My mean is 78, almost 79%. My standard deviation is 18%. I want to make matters easy for myself. So let's just say for the moment that the true sample average is 80%, and the true standard deviation is 20%. So let's create a model based on this. So what's going to happen is I'm going to be sampling fixed sample size from some distribution and calculating the mean each time. And let's say I fix again the sample size at 44. I have here a sample. This is from fall 2011. And let's say I'm going to calculate the sample average. So I'm going to calculate the sample average of fall 2011. In this case, it was 80.8%. That was the sample average. So if I'm saying the true average is 80%, certainly this value is right where it should be. So in fact, I got very close to where I thought I should be getting. Now, again, I'm saying also the true standard deviation again, but the true mean, I mean mu, and the true standard deviation is lowercase sigma. The population mean, population standard deviation, and let's say that it's 0.2. Now this number comes from the sampling distribution of the mean. This number here is the mean of individual values. This standard deviation is the standard deviation of true values. And if there's any indication from our sample, it looks like that this distribution is left skewed. But what does the sampling distribution of the mean for, let's say, a sample size of 44 look like? Well, if there's no bias for these two parameters that we've listed, the true mean of the sampling distribution of the mean, boy, that's a mouthful, that's going to be still 80% if there's no bias in the way we sample. What about the standard deviation? True standard deviation for the sampling distribution of mean. Well, it's not going to be this number right here. Instead, it's going to be 0.2 divided by square root of the sample size, which is 44. And that's going to be one standard deviation for the sample mean for a sample size of 44. When I look at the distribution then, here's what it would look like. I know that the original distribution was left skewed, but what I'm saying is the central limit theorem will come into play, and a sample size of 44 should be large enough to make the sampling distribution of the mean for a sample size of 44 look more normally shaped with this standard deviation and this center. So where does our value come in? Well, our particular sample average lands right here, right next to the mean. What about other terms? Well, again, there's the fall value. Here's summer. This sample average there was 78%. What about spring 2011? The sample size, the sample mean was 87.9. What about winter 2011? Again, the sample average here was 87%. How unusual are any of these values? Well, we could look over here. Look again at our distribution. And we can see that even though, again, the sample size are not the same, this one's actually right here close, 87.9. 87.9 is about right here. How unusual is it to get 87.9 or even something more extreme if the mean of the sampling distribution of the mean is 80%? Well, let's just find that out really quick. 0.8791 minus the 80% divided by, and we said the true standard deviation was 0.2 divided by square root, and again, I'll use sample size of 44. I know that's not correct. There's my z-score. Again, I'm just going to round this just to get an idea of what we're dealing with here. So this is 0.0043. So what this is indicating that this value, if it's truly 80% passing, sample average, is unusual. So looks like we're really close to this part right here. A very unusual result if indeed the sample average, the true sample average, should be 80%.